So our new problem is a balloon is being inflated at 100 cubic centimeters per second. How fast is the radius growing when the volume is 2,000 centimeters cubed? So this balloon in particular is about the size of a 2-liter bottle, so I figured that's about 2,000 cubic centimeters. Go ahead and try to solve it using that 6-step process from before, or a spreadsheet, or both. Pause the video and come back when you're ready. Okay, here you are. So step 1, draw a picture and make it mathematical. Balloons are not entirely spherical, but a sphere is probably the simplest reasonable approximation. So let's say it's a sphere. And you might say, well, it's not a sphere, that's wrong. But it's better to do a quick approximation and be pretty close to right than not have any answer at all in a lot of problems. So we'll draw the world's best sphere here and make it mathematical by putting a radius on it and saying it has some volume. And then step 2, write down the names and values that we know. Let's see, the volume is 2,000 cubic centimeters. The radius, we actually don't know yet. And any rates, do we know dv dt? Do we know dr dt? Well, if the balloon's being inflated at some volume amount per second, that sounds like dv dt, so we'll put 100 cubic centimeters per second there. And it's asking about how fast the radius is growing, so we actually don't know that yet. Here in step 2, we're only listing things that are known. In step 3, we want to know dr dt. In step 4, write a formula or equation for the situation, but not substituting known values yet. So what's an equation that describes this? Well, you might remember the volume of a sphere is 4/3 pi r cubed. Step 5, find a rate by taking a derivative. So we can say d dt of volume equals d dt 4/3 pi r cubed. And d dt of volume, that's just d dt of volume. We can't do anything with that. Or, I mean, we could call it dv dt. What can we do with 4/3 pi r cubed? Do we need the product rule? Nope. 4/3 is a constant, pi is a constant, and they're multiplying stuff, so it's 4/3 pi. And then what's d dt of r cubed? Well, we can write it that just to show that we moved the constant. So we still got dv dt, 4/3 pi, and if this was ddr of r cubed, then it would just be 3r squared, but it's ddt of r cubed, so we'll say it's 3r squared times ddt of r, or dr dt. And then step 6, so I guess we can just say this is dr dt. Step 6, solve the result of step 5 for what you want, which was listed in step 3. We want dr dt. So how do I solve this for dr dt? Just divide both sides by this stuff. So we'll have dv dt times 1 over 4/3 pi times 3r squared equals dr dt. Yeah, I could have canceled the 3 with the 3 there, but you don't need to. All right, and then we're going to plug in values from step 2. We know that v equals 2,000. We know dv dt equals 100 cubic centimeters per second. Oh, actually, let's check units. dv dt is cubic centimeters per second. 4/3 is unitless, pi is unitless, 3 is unitless. R squared would be centimeters squared, and dr dt would be centimeters per second. So does that all work out? I've got centimeters squared on the bottom, centimeters cubed on the top, and so that ends up with just centimeters on the top and seconds on the bottom. So units check out. Now we know dv dt, we know 4/3, we know pi, we know 3. We don't actually know r at this point. We had that as a question mark up at the top. So how can we solve that? Let's make a kind of sidebar here. We know that v equals 4/3 pi r cubed, and we know that v is 2000. Let's solve v equals 4/3 pi r cubed for r. So we divide both sides by 4/3 and then take the cube root. So we'd say v times 1 over 4/3 pi equals r cubed, and then take the cube root. V times 1 over 4/3 pi equals r. So at this point I would plug in 2000 for v, and that would get r. I would actually do all that in Desmos all in one spot, so I don't have to type in new numbers from the calculator based on numbers I had already gotten. So let's go check that. All right, here we are in Desmos. I thought of a way to say dv dt by saying the rate of v. I guess that's good enough. So we've got our volume change rate here, our initial volume here, and we're trying to compute our initial radius using the formula we came up with, basically inverting the volume of a sphere formula. This 0 theta thing, Desmos is trying to do polar coordinates because it recognizes r as a radius, but we don't really have polar coordinates going on here. And then the formula we got for the rate of change of radius was this by implicit differentiation, and using the values we have there, it gives us 0.13 centimeters cubed, centimeters per second. Another way of doing it is to say, here's the volume at time t. It's the initial volume plus the rate of change times how much time. And here's the radius at time t. I'm using capital R to avoid using lowercase r like we did there. And then we can ask, what's the rate of change of the radius? What's that function? And we get, here's the radius at time t. It's growing kind of like the same shape as a cube root. Plain cube root would start at 0, 0, but here our volume started at 2000 at time 0. So that's why we're not seeing that kind of usual cube root starting at the origin. And we can say, what does the rate of change look like? It seems to be falling off. And then we can ask, what's the rate of change of radius at time 0? We get 0.13, and we got 0.13 there. So it's always nice when you do something sort of two different ways and get the same answer. Speaking of trying something different ways and getting the same answer, can you lay this out in a spreadsheet? So let's try that. So hopefully you've tried it in a spreadsheet. If you haven't yet, go try, pause the video and come back. Here's how I would lay it out. I'd have time in seconds. I'd have delta t. I would have the volume. I would have the rate of change of the volume. I'd have the radius and dr dt. So maybe that's enough of a hint to go try it in a spreadsheet. So that's what we'll try next. All right, here we are in a spreadsheet. So we've got our numbers, got the same layout I just suggested. We can compute delta t. And then what's the formula for the radius if we already know the volume? Remember, that was current volume divided by 4/3 times pi, and then that whole thing to the 1/3 to take the cube root. And then what's the new volume based on the old volume? It's the old volume plus how quickly we're inflating times delta t. And then copy the formula for r, compute the new radius, and then the rate of change of radius is new minus old over delta t. And that's pretty much what we got in Desmos 0.13026, 0.13005. We can make delta t much smaller, and then we get basically the same thing. All right, we think that problem is solved.